So we had a look into part of what a dot and cross diagram looks like. And dot and cross diagrams are basically used to show what happens during ionic bonding and to show the electron transfers that take place. What we do is represent the electrons from one type of atom as crosses and the electrons from the other type of atom as dots. This way we can see which atoms the electrons in an ion have come from. So we didn't do that for this example. There are no crosses in this diagram. Fair enough. But I'm going to show you 3 examples of dot and cross diagrams for ionic bonding in structures. The first one looks at magnesium chloride. So we have one metal magnesium atom and 2 non-metal chlorine atoms. The 2 electrons on the outer shell of magnesium will transfer and will be split between the 2 chlorine atoms. Each chlorine will gain 1 electron and so what this does is turn each chlorine atom into a 1- chloride ion. The magnesium, on the other hand, has lost 2 electrons. We removed that entire outer shell because there were no electrons on it. So the magnesium's lost 2 electrons and has a 2+ charge as a result. The good thing about these diagrams is you can see exactly where the electrons have come from because of these dots and crosses. We have the dots coming from magnesium and the crosses coming from chlorine. So these 3 ions of 2 different charges will attract each other. And we call this attraction electrostatic attraction. So the ionic bonds hold together due to the electrostatic attraction of oppositely charged ions. The next example looks at calcium oxide. Calcium is a group 2 element and oxygen is a group 6 element. Calcium loses its 2 electrons, which are then gained by the group 6 element oxygen. So we can remove this outer shell, these arrows. And what we have is a 2+ calcium ion formed, and okay, get these out of the way. A 2- oxide ion. These ions attract each other, and this is how the ionic bond forms. And we draw brackets around the ions and have the charges written above them. The last example is sodium oxide. In this situation, we have 2 sodium ions for every 1 oxide ion. Sodium is in group 1, and of course, oxygen is in group 6. Sodium has 1 electron on its outer shell. The electrons in both outer shells of these sodium ions are lost, and they are both gained by the oxygen. The 2 sodium ions form +1 ions, the 2 sodium atoms form +1 ions, having lost an electron each, and the oxygen forms a 2- oxide, having gained these 2 electrons. So now I'm going to run through some ions and their names, as well as looking at some of the ionic compounds that we can form from these ions. But first, a bit of information on actually naming them. So if an ion ends in IDE, ends in ide, it is a negatively charged simple ion. So some negative ions formed from single atoms or single elements include the oxide ion and the sulfide ion. These are ions of oxygen and sulfur in group 6. The ions formed from group 7 elements are known as halides. Fluoride, chloride, and bromide are very common examples. There is one exception to this rule, and that is the hydroxide ion. Now, this isn't an ion which is formed from one element, but it is actually made up of oxygen and hydrogen, and has a 1- charge. Speaking of oxygen, if an ion ends in ATE, 8, this means we have an ion which is negatively charged and is made up of oxygen and one other element. For example, nitrogen is made up of oxygen and nitrogen. Carbonate is made up of, or the carbonate ion is made up of oxygen and carbon, and sulfate is made up of oxygen and sulfur. Now you need to be able to work out the formula of ionic compounds given the ions. This is in most cases not difficult at all, and I've actually listed a series of positive and negatively charged ions that we're going to use to form some ionic compounds. And ionic compounds are neutral, so this is all about balancing out the charges of the ions to 0. And like I said, this is mostly quite simple. For example, a sodium ion and a chloride ion, you will only need one of each to form the ionic compound sodium chloride. Both have single charges but just opposite signs, so you only need one of each. And it's a similar thing with something like calcium and oxide. If two ions have the same number next to their charge but just opposite signs, you will only need one of each to form an ionic compound which is neutral. For things like calcium and, let's say, nitrate, you're going to need 2 nitrate ions for every 1 calcium ion. We've got 1 ion which has a charge of 2+, and we've got 2 ions which have a charge of 1-. 2 plus 2 times -1 is 0. Probably the hardest one that you could get would be a compound made up of 2 ions of charge sizes 2 and 3. So let's say aluminium and our carbonate ion. Aluminium has a charge of 3+, and our carbonate ion has a charge of 2-. A very good way to work out the formula here is to reflect the charges onto how many of each ion there is. And what do I mean by that? Well, if we look at aluminium, the charge on the other ion is 2-. So we say that there are 2 aluminium ions in this formula. And for carbonate, the charge on the other ion, not carbonate, aluminium, is 3. So we give this formula 3 carbonate ions. And that might seem quite strange, but it is quite a simple trick. This formula is correct, and that method does work every time. You can add up the charges to check. You've got 3 ions of charge 2-, and you've got 2 ions of charge 3. You've got 2 ions of charge plus 3. 3 times minus 2 plus 2 times 3 is 0. And this would work if you had two ions of charges minus 3 and plus 2. All you do is take the number next to the ion, assign it to how many of the other ions you have in the formula. So I've spoken about how ions are attracted to each other in ionic bonds, but not about the actual structure of ionic compounds. How do these compounds actually exist in the world? Well, they don't exist as individual molecules. So if we have sodium chloride, we wouldn't have one sodium chloride separate from another one. In reality, ionic compounds have a structure we would call a giant ionic lattice. So we have a regular arrangement of billions of oppositely charged ions closely packed together. And we can say, for example, that these purple particles are sodium ions and the green ones are chloride ions. The electrostatic forces of attraction that we spoke about earlier occur in all directions, and instead of having one positive ion attracted to one negative ion, the attractions act in all directions. So this sodium ion here is attracted to all chloride ions surrounding it. The chloride ions are attracted to all the sodium ions surrounding them as well. A correct ratio of positive to negative ions is still maintained, and there are repulsions between ions of the same charge. But overall, the forces of attraction are stronger than the forces of repulsion, and that is what keeps this lattice intact. Now, this is one of a few ways in which ionic compounds can be represented through models. And we're going to do a bit of a summary, looking at some other ways, and we're going to start with dot and cross diagrams. So dot and cross diagrams are very good for showing how electrons are transferred and how ions are formed. This is obviously the basis for ionic bonding, but it doesn't actually show in any way the large 3D lattice and how these ions are arranged in compounds. Just looking at this, you might assume that ionic bonding is between 2 or 3 individual ions, and that is an ionic compound, and this is obviously not the case. The model also doesn't show the relative sizes of the ions, so that's another thing. Now, something we haven't seen before is a model called the ball and stick model. This one does give a 3D representation of the ionic lattice, and it also shows an inner layer of this lattice. That's essentially what lattice is. It's millions of layers of ions on top of each other. And you can actually see, if you look at this green ion in the middle here, there are 6 ions of opposite charge to which this green particle is directly attracted to. And so that's what we mean when I said there was electrostatic attractions in all directions. And this is true of every single ion in this lattice except maybe some which are on the edges. Unfortunately, the model does suggest that there are large gaps between the ions when in reality they're packed together very closely. Finally, the other 3D model we looked at on the last page gives a good idea of the 3D structure of ions in terms of how closely packed together they are in the lattice, but because there are no spaces between the ions, we can't actually see any inner layers, but only these outer ones. So these models all have their benefits. I'd say if you want to learn more about how simple ions are actually formed in terms of electron transfer in the first place, then the dot and cross diagram would be best. But for learning about how ions are arranged in a lattice, it would have to be between these two.